Hello everyone. The title of today's talk is Strong Average Case Circular Bounds from Non-Trivial Derandomization. This is a joint work with Li Jiechen from MIT. So our first motivation is to prove some circular bounds. People wanted to prove P not equal to NP by proving circular bounds, and this is just how a typical circuit might look like. So if you want to prove circular bounds, you pick a hard function and you argue that every small enough circuit cannot compute your function. And if you can prove NP does not have polynomial size circuits, then you can prove P not equal to NP. But currently it's even open whether NP has linear size circuits, so the progress in this direction is very small. Therefore, people turn their attention to restricted version of circuits such as AC0. AC0 means constant depth and or not circuits where AND gates and OR gates have unbounded phi-in. A line of work established stronger bounds for AC0, and in particular, they show that the parity function cannot be computed by polynomial size AC0. Parity is the function that outputs 1 if the number of ones in the input is odd. Now we want to prove circular bounds for stronger classes. What about adding parity to AC0? In general, we have the circuit class AC0P, which is AC0 extended with mod P gates, and mod P is the function that outputs 1 if P does not divide the number of ones in the input. We can see that mod 2 is just a parity, and AC0 with parity is just AC02. Rasborov and Smolsky proved strong lower bounds for AC0P when P is a prime. And in particular, the function mod 3 cannot be computed by polynomial size AC02 circuits. Now we want to prove even lower bounds for even stronger classes. So what about adding mod 3 to AC02? This circuit class is equivalent to AC06, which is AC0 equipped with mod 6 gates. This circuit class doesn't seem much stronger than AC02, but unfortunately, it has been open for over 20 years to find a function in NEXP that cannot be computed by some restricted version of AC06. Recall that NEXP is a very, very large class. It's a class of languages computed by non-deterministic exponential time algorithms. So it's actually a very large class. But it seems difficult to find, even in this very large class, a function that cannot be computed by this seemingly very restricted computational model. So until 2011, Williams proved NEXP does not have polynomial size ACC0 circuits. ACC0 is the union of AC0M for all constant m, so this m can possibly be a composite number. And AC0M is just AC0 extended with mod m gates. This lower bound is proven by the so-called Algorithmic Method, which roughly says that non-trivial circuit analysis algorithms imply circular bounds. So what are non-trivial circuit analysis algorithms? Let's define circuit analysis problem first. Two problems that will be considered in this talk are C-set and C-cap, where C is a circuit class. In C-set, you are given the description of a C circuit, and you want to find if this circuit accepts some input. And in C-cap, you are also given the description of a C circuit, and you want to estimate the probability that the circuit accepts a random input. And you are allowed to have an additive error of epsilon. Here, this epsilon is typically a constant such as 0.1, but in this talk, the epsilon of cap would be something like inverse polynomial. Notice that this cap is actually very easy if you have randomized algorithms. You can just pick a bunch of x and you output the empirical probability that C accepts your picked x. So the point of C-cap is to design good deterministic algorithms, or in other words, this C-cap is essentially a derandomization problem. Now we can define non-trivial circuit analysis algorithms. For both problems, we have trivial algorithms that run in time 2 to n time poly of the size of input circuit. You simply try every possible assignment. And for a circuit analysis algorithm to be non-trivial, you only need to shave a super poly n factor from this trivial running time. So if the running time is slightly less than 2 to n, then we say your algorithm is non-trivial. The algorithmic method says that if we have non-trivial set or cap algorithm for C circuits, then NEXP does not have polynomial set C circuits. Here there are some technical constraints on this circuit class C, but we will not elaborate them in this talk. Williams proved that there is a non-trivial ACC0 set algorithm, so he concludes that NEXP does not have polynomial set ACC0 circuits. And there are some subsequent developments of this lower bound. Chen, Oliveira, and Susanna proved that NEXP cannot be half plus 1 over per log n approximated by polynomial set ACC0 circuits. This lower bound means that you can pick a language L in NEXP such that for every polynomial set ACC circuits, it only agrees with L on at most half plus 1 over per log n fraction of inputs. Notice that if you only want to agree with some language on half inputs, then you always have a trivial circuit that do the job. So this lower bound essentially means that if you only have polynomial set ACC0 circuits, then you cannot do much better than this trivial bound of half. And Murray and Williams proved that non-deterministic quasi-polynomial time, or NQP, does not have polynomial set ACC0 circuits. It makes the NEXP much smaller. And Chen proved that NQP cannot be half plus 1 over per log n approximated by polynomial set ACC0 circuits. It extends this lower bound to the average case. There is a very natural question, that is, can we improve this to half plus 1 over poly n? This is not only motivated by circular bounds, it also has some impact on derandomization. So people wanted to prove P equal to BPP by building pseudorandom generators or PRGs. PRG is just a deterministic algorithm that stretches some short random bits to some long pseudorandom bits. Suppose we have some adversary circuit. We say this PRG fools this adversary if the following is true. First, we compute the probability that the adversary accepts true random inputs, and then we compute the probability that the adversary accepts pseudo-random inputs, which is induced by a true random seed and this PRG. So, if these two probabilities are close to each other, then we say that this PRG fools the adversary. Now, suppose we have an adversary that implements some randomized algorithm, and we have a PRG that fools this algorithm, fools this adversary. Then we can derandomize the algorithm. We simply run this adversary against each of the pseudo-random output of the PRG. Notice that the seed length is s, so there are only 2 to s such pseudo-random outputs. So we only need to run this adversary for 2 to s time, then we can derandomize it. So if we want to prove P equal to BPP, then we need to have a PRG for general circuits with log n seed length. However, it seems that we are far from this goal. Currently, we don't even have PRGs for AC02 with subpolynomial seed length. So why? One reason is that we don't have strong enough average case lower bounds against AC02. Nisa and Wilderson showed that if we have a hard enough function, then we can build a PRG from this hard function. However, if we want to use this method to build PRG for AC02, then we need a hard function that cannot be half plus 1 over n approximated by AC02. We don't have such strong lower bounds. Currently, we only know that majority cannot be half plus 1 over n to 0.49 approximated by S02. And even if we consider large classes such as exponential time, we don't know if every language in exponential time can be half plus 1 over square root n approximated by S02. So our lower bounds are not strong enough. In this work, we prove strong average case circular bound for ACC0. Our main result is that non-dimensional quasi-polynomial time cannot be half plus inverse polynomial approximated by polynomial sets ACC0 circuits. This improves the half plus 1 over per log n result by Chen and surpasses the half plus 1 over square root n barrier for AC02. We also have a meta-theorem saying that if we have non-trivial cap algorithm for C circuits, then an EXP cannot be half plus inverse polynomial approximated by C. Notice that the cap here requires an error parameter of inverse polynomial. So how would we prove such a low bound? Our first attempt is to use Hardness amplification. Given a function f, we amplify it to a function amp of f, and given an oracle O that half plus inverse polynomial approximates amp of f, we can construct an O oracle circuit that 0.99 approximates f. In other words, if we want to prove amp of f cannot be half plus inverse polynomial approximated, then we only need to prove f cannot be 0.99 approximated. And we already have 0.99 lower bounds for AC0. So it seems that we should already have half plus inverse polynomial lower bound for AC0. Actually, no. The reason is that the oracle circuit is actually a TC0 oracle circuit. TC0 means constant depth circuits with majority gates of unbounded fan-in. In addition, in some sense, these majority gates are necessary. So it means that if O can be implemented in ACC0, then we only know that there is a TC0 circuit that can approximate F. So it means that if we want to prove a strong average case lower bound for ACC0, then we need to start with a TC0 lower bound. And we don't have such good TC0 lower bounds. So this plan failed. Anyway, let's see how Chen proved the 0.99 lower bound. Of course, it's proven by contradiction, and we assume that NQP can be 0.99 approximated by ACC0. And in particular, NC1 can be 0.99 approximated by ACC0. Here, NC1 means polynomial set formulas. It's a subclass of P. Then, using some good self-reducibility properties for NC1, Chen proves that under this assumption, NC1 can be simulated by AC0. That is, NC1 is equivalent to AC0. And as we have non-trivial algorithms for AC0, we also have non-trivial algorithms for NC1. Notice that this step is non-trivial and requires PCPP, but anyway, let's just assume it's true. And since we have non-trivial algorithm for NC1, we can use the algorithmic method to prove that NQP cannot be 0.99 approximated by NC1. This is actually the main body of algorithmic method, and it took Chen about 4 sections to prove this. But in this talk, we will just treat it as a black box. NC1 can compute majority, so we can use Hardness amplification in the previous slide to amplify this 0.99 lower bound into NQP cannot be half plus inverse polynomial approximated by NC1. Still, we need to deal with step 1. That is, assuming NC1 can be 0.99 approximated by ACC0, then NC1 can be simulated by ACC0. If we want to prove a strong average case lower bound for ACC0, we can only assume that NC1 can be half plus inverse polynomial approximated by ACC0. Can we simulate NC1 by ACC0 now? The majority issue arises again. So if NC1 can be half plus epsilon approximated by ACC0, then our simulation of NC1 would need majority gates with fan-in 1 over epsilon. If epsilon is a constant, then we are good with that, because this phi-in is also a constant. But if epsilon is inverse polynomial, then this phi-in is polynomial, and we conjecture that polynomial set ACC0 cannot compute majority gates with polynomial phi-in. So we cannot simulate NC1 by ACC0. With some efforts, we can show that under this condition, we can simulate NC1 by majority of ACC0. That is like such a circuit. We can push the majority gates in our simulation into the very top of the circuit, and the bottom are just ACC0 circuits. So we still need a circuit analysis algorithm for majority of ACC0 to proceed, but unfortunately, we don't know how to do circuit analysis for this class. Our solution is to use approximate sum, which is something weaker than majority. So let me introduce this approximate sum. First, let C be a circuit class. A linear sum of C is just a linear combination of some circuits from C. So this linear sum receives a Boolean input, and for each bottom circuit, it has an output either 0 or 1 on this input, and we treat these zeros and ones as real numbers. We compute a linear sum of them and obtain a real number as the final output. That is, a linear sum receives a Boolean string as an input and outputs a real number. Now, let f be a Boolean function. We say f is an approximate sum of C if there is a linear sum such that it's very close to f on L infinity norm. That is, for any input, if fx is 0, then this linear sum is very close to 0, and if fx is 1, then this linear sum is very close to 1. There are two advantages of approximate sum. The first is that we can do circuit analysis of approximate sum if we can do circuit analysis for the bottom Ci. For example, for CAP algorithms, if we can estimate the accept probability of each bottom Ci, then we just compute a weighted sum of these accept probabilities, and it should be very close to the acceptability of the approximate sum. And as we have good algorithm for approximate sum of ACC0, by using a variant of algorithmic method, Chen and Williams proved that NQP cannot be computed by approximate sum of ACC0. So the approximate sum of ACC0 is actually a good class. We have good algorithms and good lower bounds for them. The second advantage of approximate sum is it can do some hardness amplification. In our paper, we proved that there are languages A and B such that if A cannot be worst case computed by approximate sum of ACC0, then B cannot be half plus inverse polynomial approximated by ACC0. So the A and B are somewhat good problems. Both of them are NC1 hard and in polynomial time. If we read this hardness amplification theorem in contrapositive, then it's like if B can be half plus inverse polynomial approximated by ACC0, then NC1 collapses to approximate sum of ACC0. So we can proceed to our final proof. Of course, it's also proven by contradiction. So we assume NQP can be half plus inverse polynomial approximated by ACC0, and in particular, B, as it's in polynomial time, can also be half plus inverse polynomial approximated by ACC0. And by the previous collapse theorem, NC1 can be simulated by approximate sum of ACC0. So these two classes are the same class. And as we have non-trivial algorithm for approximate sum of ACC0, we can also construct a non-trivial algorithm for NC1. Then we use the standard algorithmic method to prove that NQP cannot be half plus inverse polynomial approximated by NC1, which is a contradiction. So our conclusion is that NQP cannot be half plus inverse polynomial approximated by ACC0. Now, after our work, there are some new developments. Chen, Liu, and Williams proved that E to NP cannot be half plus inverse sub-exponential approximated by AC0 circuits of sub-exponential size. For comparison, we only proved such a low bound for a size function of sub-half exponential size, which is much weaker than this sub-exponential size bound. And another amazing aspect of the low bound is it holds for almost every input length. For comparison, lower bounds proven by algorithmic method typically only hold for infinitely many input lengths, including R bound, and they can prove lower bounds for almost every input length. So that's all. Thank you, and any questions?